Psychology by William James, Professor of Psychology in Harvard University, Part 1. This book is in the public domain and available freely online. Preface. In preparing the following abridgment of my larger work, The Principles of Psychology, my chief aim has been to make it more directly available for classroom use. For this purpose I have omitted several whole chapters and rewritten others. I have left out all the polemical and historical matter, all the metaphysical discussions and purely speculative passages, most of the quotations, all the book references, and, I trust, all the impertinences of the larger work, leaving to the teacher the choice of orally restoring as much of this material as may seem to him good, along with his own remarks on the topics successively studied. Knowing how ignorant the average student is of physiology, I have added brief chapters on the various senses. In this shorter work, the general point of view, which I have adopted as that of natural science, has, I imagine, gained in clearness by its extrication from so much critical matter and its more simple and dogmatic statement. About 2/5 of the volume is either new or written, the rest is scissors and paste. I regret to have been unable to supply chapters on pleasure and pain, aesthetics, and the moral sense. Possibly the defect may be made up in later edition, if such thing should ever be demanded. I cannot forbear taking advantage of this preface to make a statement about the composition of the principles of psychology. My critics in the main have been so indulgent that I must cordially thank them, but they have been unanimous in one reproach, namely, that my order of chapters is planless and unnatural, and in one charitable excuse for this, namely, that the work, being largely a collection of review articles, could not be expected to show as much system as a treatise cast in a single mold. Both the reproach and the excuse misapprehend the facts of the case. The order of composition is doubtless unshapely, or it would not be found so by so many. But planless it is not, for I deliberately followed what seemed to me a good pedagogic order, in proceeding from the more concrete mental aspects with which we are best acquainted to the so-called elements which we naturally come to know later by way of abstraction. The opposite order of building up the mind out of its units of composition has the merit of expository elegance and gives a neatly subdivided table of contents, but it often purchases these advantages at the cost of reality and truth. I admit that my synthetic order was stumblingly carried out, but this again was in consequence of what I thought were pedagogic necessities. On the whole, in spite of my critics, I venture still to think that the unsystematic form charged upon the book is more apparent and profound, and that we really gain a more living understanding of the mind by keeping our attention as long as possible upon our entire conscious states as they are concretely given to us, than by the post-mortem study of their comminuted elements. This last is the study of artificial abstractions, not of natural things. But whether the critics are right or I am on this first point, the critics are wrong about the relation of the magazine articles to the book. With a single exception, all the chapters were written for the book, and then by an afterthought some of them were sent to magazines, because the completion of the whole work seems so distant. My lack of capacity has doubtless been great, but the charge of not having taken the utmost pains, according to my lights, in the composition of the volumes, and not justly be laid at my door. Chapter 1 Introductory. The definition of psychology may be best given in the words of Professor Ladd, as the description and explanation of states of consciousness as such. By states of consciousness are meant such things as sensations, desires, emotions, cognitions, reasonings, decisions, volitions, and the like. Their explanation must, of course, include the study of their causes, conditions, and immediate consequences so far as these can be ascertained. Psychology, to be treated as a natural science in this book, this requires a word of commentary. Most thinkers have a faith that at bottom there is but one science of all things, and that until all is known, no one thing can be completely known. Such a science, if realized, would be philosophy. Meanwhile, it is far from being realized, and instead of it, we have a lot of beginnings of knowledge made in different places and kept separate from each other merely for practical convenience sake, until with later growth they may run into one body of truth. These provisional beginnings of learning we call the sciences in the plural. In order not to be unwieldy, every such science has to stick to its own arbitrarily selected problems, and to ignore all others. Every science thus accepts certain data unquestioningly, leaving it to the other parts of philosophy to scrutinize their significance and truth. All the natural sciences, for example, in spite of the fact that farther reflection leads to idealism, assume that a world of matter exists altogether independently of the perceiving mind. Mechanical science assumes this matter to have a mass and to exert a force, defining these terms merely phenomenally, and not troubling itself about certain unintelligibilities which they present on nearer reflection. Motion similarly is assumed by mechanical science to exist independently of the mind, in spite of the difficulties involved in the assumption. So physics assumes atoms, action at a distance, etc. Uncritically, chemistry uncritically adopts all the data of physics, and physiology adopts those of chemistry. Psychology is, and natural science deals with things in the same partial and provisional way. In addition to the immaterial world with all its determinations, which other sciences of nature assume, she assumes additional data peculiarly her own, and leaves it to more developed parts of philosophy to test their ulterior significance and truth. These data are 1. Thoughts and feelings, or whatever other names transitory states of consciousness may be known by. 2. Knowledge, by these states of consciousness, of other things. These things may be material objects and events or other states of mind. The material objects may be either near or distant in time and space, and the states of mind may be those of other people, or of the thinker himself at some other time. How one thing can know another is the problem of what is called the theory of knowledge. How such a thing as a state of mind can be at all is the problem of what has been called rational, as distinguished from empirical psychology. The full truth about states of mind cannot be known until both theory of knowledge and rational psychology have said their say. Meanwhile, an immense amount of provisional truth about them can be got together, which will work in with the larger truth and be interpreted by it when the proper time arrives. Such a provisional body of propositions about states of mind and about the cognitions which they enjoy is what I mean by psychology considered as a natural science. On any ulterior theory of matter, mind, and knowledge, the facts and laws of psychology thus understood will have their value. If critics find that this natural science point of view cuts things too arbitrarily short, they must not blame the book which confines itself to that point of view, but rather must they go on themselves to complete it by their deeper thought. Incomplete statements are often practically necessary. To go beyond the usual scientific assumptions in the present case would require not a volume, but a shelfful of volumes, and by the present author such a shelfful could not be written at all. Let it also be added that the human mind is all that can be touched upon in this book. Although the mental life of lower creatures has been examined into of late years with some success, we have no space for its consideration here, and can only allude to its manifestations incidentally when they throw light upon our own. Mental facts cannot be properly studied apart from the physical environment of which they take cognizance. The great fault of the older rational psychology was to set up the soul as an absolute spiritual being with certain faculties of its own by which the several activities of remembering, imagining, reasoning, willing, etc. were explained almost without reference to the peculiarities of the world with which these activities deal. But the richer insight of modern days perceives that our inner faculties are adapted in advance to the features of the world in which we dwell. Adapted means so as to secure our safety and prosperity in its midst. Not only are our capacities for forming new habits, for remembering sequences, and for abstracting general properties from things, and associating their usual consequences with them, exactly the faculties needed for steering us in this world of mixed variety and uniformity, but our emotions and instincts are adapted to very special features of that world. In the main, if a phenomenon important for our welfare, it interests and excites us the first time we come into its presence. Dangerous things fill us with involuntary fear, poisonous things with distaste, indispensable things with appetite. Mind and world, in short, have been evolved together, and in consequence are something of a mutual fit. The special interactions between the outer order and the order of consciousness, by which this harmony, such as it is, may in the course of time have come about, have been made the subject of many evolutionary speculations, which, though they cannot so far be said to be conclusive, have at least refreshed and enriched the whole subject, and brought all sorts of new questions to the light. The chief result of all this more modern view is the gradually growing conviction that mental life is primarily teleological, that is to say, that our various ways of feeling and thinking have grown to be what they are because of their utility in shaping our reactions on the outer world. On the whole, few recent formulas have done more service in psychology than the Spencerian one that the essence of mental life and bodily life are one, namely, the adjustment of inner to outer relations. The adjustment is to immediately present objects in lower animals and in infants. It is to objects more and more remote in time and space, and inferred by means of more and more complex and exact processes of reasoning when the grade of mental development grows more advanced. Primarily then, and fundamentally, mental life is for the sake of action of a preservative sort. Secondarily and incidentally it does many other things, and may even, when ill adapted, lead to its possessor's destruction. Psychology, taken in the widest way, ought to study every sort of mental activity, the useless and harmful sorts as well as that which is adapted. But the study of the harmful in mental life has been made the subject of a special branch called psychiatry, the science of insanity. And the study of the useless is made over to aesthetics. Aesthetics and psychiatry will receive no special notice in this book. All mental states, no matter what their character as regards utility may be, are followed by bodily activity of some sort. It lead to inconspicuous changes in breathing, circulation, general muscular tension, and glandular or other visceral activity, even if they do not lead to conspicuous movements of the muscles of voluntary life. Not only certain particular states of mind, then, such as those called volitions, for example, but states of mind, such, all states of mind, even mere thoughts and feelings, are motor in their consequences. This will be made manifest in detail as our study advances. Meanwhile, let it be set down as one of the fundamental facts of the science with which we are engaged. It was said above that the conditions of states of consciousness must be studied. The immediate condition of state of consciousness is an activity of some sort in the cerebral hemispheres. This proposition is supported by so many pathological facts and laid by physiologists at the base of so many of their reasonings that to the medically educated mind it seems almost axiomatic. It would be hard, however, to give any short and peremptory proof of the unconditional dependence of mental action upon neural change. That general and usual amount of dependence exists cannot possibly be ignored. One has only to consider how quickly consciousness may be, so far, as we know, abolished by blow on the head, by rapid loss of blood, by an epileptic discharge, by full dose of alcohol, opium, ether, or nitrous oxide, or how easily it may be altered in quality by smaller dose of any of these agents or of others, or by fever, to see how at the mercy of bodily happenings our spirit is. A little stoppage of the gall duct, a swallow of cathartic medicine, a cup of strong coffee at the proper moment, will entirely overturn for the time a man's views of life. Our moods and resolutions are more determined by the condition of our circulation than by our logical grounds. Whether a man shall be a hero or a coward is a matter of his temporary nerves. In many kinds of insanity, though by no means in all, distinct alterations of the brain tissue have been found. Destruction of certain definite portions of the cerebral hemispheres involves losses of memory and of acquired motor faculty of quite determinate sorts, to which we shall revert again under the title of aphasias. Taking all such facts together, the simple and radical conception dawns upon the mind that mental action may be uniformly and absolutely a function of brain action, varying as the latter varies, and being to the brain action as effect to cause. This conception is the working hypothesis which underlies all the physiological psychology of recent years, and it will be the working hypothesis of this book. Taken absolutely, it may possibly be too sweeping, a statement of what in reality is only a partial truth, but the only way to make sure of its unsatisfactoriness is to apply it seriously to every possible case that can turn up. To work an hypothesis that for all it is worth is the real, and often the only, way to prove its insufficiency. I shall therefore assume without scruple at the outset that the uniform correlation of brain states with mind states is a law of nature. The interpretation of the law in detail will best show where its facilities and where its difficulties lie. To some readers such an assumption will seem like the most unjustifiable, a priori materialism. In one sense it doubtless is materialism. It puts the higher at the mercy of the lower. But although we affirm that the coming to pass of thought is a consequence of mechanical laws, for, according to another working hypothesis, that namely of physiology, the laws of brain action are at bottom mechanical laws, we do not in the least explain the nature of thought by affirming this dependence, and in that latter sense our proposition is not materialism. The authors who most unconditionally affirm the dependence of our thoughts on our brain to be a fact are often the loudest to insist that the fact is inexplicable, and that the intimate essence of consciousness can never be rationally accounted for by any material cause. It will doubtless take several generations of psychologists to test the hypothesis of dependence with anything like minuteness. The books which postulate it will be to some extent on conjectural ground. But the student will remember that the sciences constantly have to take these risks and habitually advance by zigzagging from one absolute formula to another which corrects it by going too far the other way. Present psychology is on the materialistic tack and ought in the interests of ultimate success to be allowed full headway even by those who are certain she will never fetch the port without putting down the helm once more. The only thing that is perfectly certain is that when taken up into the total body of philosophy, the formulas of psychology will appear with a very different meaning from that which they suggest so long as they are studied from the point of view of an abstract and truncated natural science, however practically necessary and indispensable their study from such a provisional point of view may be. The divisions of psychology, so far as possible, Then, we are to study states of consciousness in correlation with their probable neural conditions. Now the nervous system is well understood today to be nothing but a machine for receiving impressions and discharging reactions preservative to the individual and his kind. So much of physiology the reader will surely know. Anatomically, therefore, the nervous system falls into three main divisions, comprising 1. The fibers which carry currents in, 2. The organs of central redirection of them, and 3. The fibers which carry them out. Functionally, we have sensation, central reflection, and motion to correspond to these anatomical divisions. In psychology, we may divide our work according to a similar scheme and treat successively of three fundamental conscious processes, their conditions. The first will be sensation, the second will be cerebration or intellection, the third will be the tendency to action. Much vagueness results from this division, but it has practical conveniences for such a book as this, and they may be allowed to prevail over whatever objections may be urged. Chapter 2. Sensation in general. Incoming nerve currents are the only agents which normally affect the brain. The human nerve centers are surrounded by many dense wrappings of which the effect is to protect them from the direct action of the forces of the outer world. The hair, the thick skin of the scalp, the skull, and two membranes at least, one of them, a tough one, surround the brain, and this organ moreover, like the spinal cord, is bathed by a serous fluid in which it floats suspended. Under these circumstances the only things that can happen to the brain are 1. The dullest and feeblest mechanical jars, 2. Changes in the quantity and quality of the blood split, and 3. Currents running in through the so-called afferent or centripetal nerves. The mechanical jars are usually ineffective. The effects of the blood changes are usually transient. The nerve currents, on the contrary, produce consequences of the most viable sort, both at the moment of their arrival and later through the invisible paths of escape which they plow in the substance of the organ and which, as we believe, remain as more or less permanent features of its structure, modifying its action throughout all future time. Each afferent nerve comes from a determinate part of the periphery and is played upon and excited to its inward activity by a particular force of the outer world. Usually it is insensible to other forces. Thus the optic nerves are not impressible by air waves, nor those of the skin by light waves. The lingual nerve is not excited by aromatic effluvia. The auditory nerve is unaffected by heat. Each selects from the vibrations of the outer world some one rate to which it responds exclusively. The result is that our sensations form a discontinuous series, broken by enormous gaps. There is no reason to suppose that the order of vibrations in the outer world is anything like as interrupted as the order of our sensations. Between the quickest audible airwaves, 40,000 vibrations, a second at the outside, and the slowest sensible heat waves, which number probably billions, nature must somewhere have realized innumerable intermediary rates which we have no nerves for perceiving. The process in the nerve fibers themselves is very likely the same, or much the same, in all the different nerves. It is the so-called current, but the current is started by one order of outer vibrations in the retina and in the ear, for example, by another. This is due to the different terminal organs with which the several afferent nerves are armed, just as we arm ourselves with a spoon to pick up soup and with a fork to pick up meat. So our nerve fibers arm themselves with one sort of end apparatus to pick up air waves, with another to pick up ether waves. The terminal apparatus always consists of modified epithelial cells with which the fiber continuous. The fiber itself is not directly excitable by the outer agent which impresses the terminal organ. The optic fibers are unmoved by the direct rays of the sun. The cutaneous nerve trunk may be touched with ice without feeling cold. The fibers are mere transmitters. The terminal organs are so many imperfect telephones into which the material world speaks, and each of which takes up but a portion of what it says the brain cells at the fiber. Central and are as many others at which the mind listens to the far-off call. The specific energies of the various parts of the brain. 2. To a certain extent anatomists have traced definitely the paths which the sensory nerve fibers follow after their entrance into the centers, as far as their termination in the gray matter of the cerebral convolutions. It will be shown on a later page that the consciousness which accompanies the excitement of this gray matter varies from one portion of it to another. It is consciousness of things seen when the occipital lobes, and of things heard when the upper part of the temporal lobes share in the excitement. Each region of the cerebral cortex responds to the stimulation which its afferent fibers bring to it in a manner with which a peculiar quality of feeling seems invariably correlated. This is what has been called the law of specific energies in the nervous system. Of course, we are without even a conjectural explanation of the ground of such a law, Psychologists, as Lewis, Rosenthal, Goldscheder, etc., have debated a good deal as to whether the specific quality of the feeling depends solely on the place stimulated in the cortex, or on the sort of current which the nerve pours in. Doubtless the sort of outer force habitually impinging on the end organ gradually modifies the end organ, the sort of commotion received from the end organ modifies the fiber, and the sort of current, a so modified fiber pours into the cortical center modifies the center. The modification of the center in turn, no man can guess how or why, seems to modify the resultant consciousness. But these adaptive modifications must be excessively slow, and as matters actually stand in any adult individual, it is safe to say that, more than anything else, the place excited in his cortex decides what kind of thing he shall feel. Whether we press the retina, or prick, cut, pinch, or galvanize the living optic nerve, the subject always feels flashes of light, since the ultimate result of our operations is to stimulate the cortex of his occipital region. Our habitual ways of feeling outer things thus depend on which convolutions happen to be connected with the particular end organs which those things impress. We see the sunshine and the fires simply because the only peripheral end organ susceptible of taking up the ether waves which these objects radiate excites those particular fibers which run to the centers of sight. If we could interchange the inward connections, we should feel the world in altogether new ways. If, for instance, we could splice the outer extremity of our optic nerves to our ears, and that of our auditory nerves to our eyes, we should hear the lightning and see the thunder, see the symphony and hear the conductor's movements. Such hypotheses as these form of good training for neophytes in the idealistic philosophy, sensation distinguished from perception. It is impossible rigorously to define as sensation, and in the actual life of consciousness sensations, popularly so called, and perceptions merge into each other by insensible degrees. All we can say is that what we mean by sensations are first things in the way of consciousness. They are the immediate results upon consciousness of nerve currents as they enter the brain, and before they have awakened any suggestions or associations with past experience. But it is obvious that such immediate sensations can only be realized in the earliest days of life. They are all but impossible to adults with memories and stores of associations acquired. Prior to all impressions on sense organs, the brain is plunged in deep sleep, and consciousness is practically non-existent. Even the first weeks after birth are passed in almost unbroken sleep by human infants. It takes a strong message from the sense organs to break this slumber. In a newborn brain this gives rise to an absolutely pure sensation, but the experience leaves its unimaginable touch on the matter of the convolutions, and the next impression which a sense organ transmits produces a cerebral reaction in which the awakened vestige of the last impression plays its part. Another sort of feeling and a higher grade of cognition are the consequence. Our ideas about the object mingle with the awareness of its mere sensible presence, we name it, class it, compare it, utter propositions concerning it, and the complication of the possible consciousness which an incoming current may arouse goes on increasing to the end of life. In general, this higher consciousness about things is called perception. The mere inarticulate feeling of their presence is sensation, so far as we have it at all. To some degree, we seem able to lapse into this inarticulate feeling at moments when our attention is entirely dispersed. Sensations are cognitive. A sensation is thus an abstraction seldom realized by itself, and the object which a sensation knows is an abstract object which cannot exist alone. Sensible qualities are the objects of sensation. The sensations of the eye are aware of the colors of things. Those of the ear are acquainted with their sounds. Those of the skin feel their tangible heaviness, sharpness, warmth or coldness, etc., etc. From all the organs of the body current may come which reveal to us the quality of pain, and to a certain extent that of pleasure. Such qualities as stickiness, roughness, etc., are supposed to be felt through the cooperation of muscular sensations with those of the skin. The geometrical qualities of things, on the other hand, their shapes, bignesses, distances, etc., so far as we discriminate and identify them, are by most psychologists supposed to be impossible without the evocation of memories from the past, and the cognition of these attributes is thus considered to exceed the power of sensation pure and simple. Knowledge of acquaintance and a knowledge about sensation, thus considered, differs from perception only in the extreme simplicity of its object or content. Its object being a simple quality is sensibly homogeneous, and its function is that of mere acquaintance with this homogeneous seeming fact. Perception's function, on the other hand, is that of knowing something about the fact. But we must know what fact we mean all the while, and the various whats are what sensations give. Our earliest thoughts are almost exclusively sensational. They give us a set of whats or that's, or it's of subjects of discourse, in other words, with the relations not yet brought out. The first time we see light in Condillac's phrase we are rather than see. But all our later optical knowledge is about what this experience gives. And though we were struck blind from that first moment, our scholarship in the subject would lack no essential feature so long our memory remained. In training institutions for the blind, they teach the pupils as much about light as in ordinary schools. Reflection, refraction, the spectrum, the ether theory, etc., are all studied, but the best taught born blind pupil of such an establishment yet lacks a knowledge which the least instructed seeing baby has. They can never show him what light is in its first intention, and the loss of that sensible knowledge no book learning can replace. All this is so obvious that we usually find sensation postulated as an element of experience, even by those philosophers who are least inclined to make much of its importance or to pay respect to the knowledge which it brings. Sensations distinguished from images, both sensation and perception, for all their difference, are yet alike in that their objects appear vivid, lively, and present. Objects merely thought of, recollected, or imagined, on the contrary, are relatively faint and devoid of this pungency, or tang, this quality of real presence which the objects of sensation possess. Now the cortical brain processes to which sensations are attached are due to incoming currents from the periphery of the body. An external object must excite the eye, ear, etc. before the sensation comes. Those cortical processes, on the other hand, to which mere ideas or images are attached are due in all probability to currents from other convolutions. It would seem, then, that the currents from the periphery normally awaken a kind of brain activity which the currents from other convolutions are inadequate to arouse. To this sort of activity, a profounder degree of disintegration, perhaps the quality of vividness, presence, or reality in the object of the resultant consciousness seems correlated. The exteriority of objects, sensation, everything or quality felt is felt in outer space. It is impossible to conceive a brightness or a color otherwise than is extended and outside of the body. Sounds also appear in space. Contacts are against the body's surface, and pains always occupy some organ. An opinion which has had much currency in psychology is that sensible qualities are first apprehended as in the mind itself, and then projected from it, or extradited, a secondary intellectual or supersensational mental act. There is no ground whatever for this opinion. The only facts which even seem to make for it can be much better explained in another way, as we shall see later on. The very first sensation which an infant gets is for him outer universe, and the universe which he comes to know in later life is nothing but an amplification of that first simple germ which, by accretion on the one hand and intussusception on the other, has grown so big and complex and articulate that its first estate is unrememberable, in his dumb awakening to the consciousness of something there, a mere this as yet, or something for which even the term this would perhaps be too discriminative, and the intellectual acknowledgment of which would be better expressed by the bare interjection hello. The infant encounters an object in which, though it be given in a pure sensation, all the categories of the understanding are contained. It has externality, objectivity, unity, substantiality, causality, in the full sense in which any later object or system of objects is these things. Here the unknown meets and greets his world, and the miracle of knowledge bursts forth, as Voltaire says, as much in the infant's lowest sensation as in the highest achievement of. In Newton's brain, the physiological condition of this first sensible experience is probably many nerve currents coming in from various peripheral organs at once, but this multitude of organic conditions does not prevent the consciousness from being one consciousness. We shall see as we go on that it can be one consciousness, even though it be due to the cooperation of numerous organs and be consciousness of many things together. The object which the numerous and pouring currents of the baby bring to his consciousness is one big blooming buzzing confusion. That confusion is the baby's universe, and the universe of all of us is still to great extent such confusion, potentially resolvable, and demanding to be resolved, but not yet actually resolved, into parts. It appears from first to last a space-occupying thing. So far as it is unanalyzed and unresolved, we may be said to know it sensationally, but as fast as parts are distinguished in it, and we become aware of their relations, our knowledge becomes perceptual or even conceptual, and as such need not concern us in the present chapter. The intensity of sensations. Light may be so weak as not sensibly to dispelled. Darkness sounds so low as not to be heard. Contact so faint that we fail to notice it. In other words, certain finite amount of the outward stimulus is required to produce any sensation of its presence at all. This is called by fetching of the law of the threshold something must be stepped over before the object can gain entrance to the mind. An impression just above the threshold is called the minimum visible, audible, etc. from this point onwards, as impressing force increases, the sensation increases also, though at slower rate, until at last an acme of the sensation is reached which no increase in the stimulus can make sensibly more great. Usually, before the acme, pain begins to mix with the specific character of the sensation. This is definitely observable in the cases of great pressure, intense heat, cold light, and sound, and in those of smell and taste less definitely so only from the fact that we can less easily increase the force of the stimuli here. On the other hand, all sensations, however unpleasant when more intense, are rather agreeable than otherwise in their very lowest degrees. A faintly bitter taste, or putrid smell, may at least be interesting. Weber's law. I said that the intensity of the sensation increases by slower steps than those by which its exciting cause increases. If there were no threshold, and if every equal increment in the outer stimulus produced an equal increment in the sensation's intensity, a simple straight line would represent graphically the curve of the relation between the two things. Let the horizontal line stand for the scale of intensities of the objective stimulus so that at 0 it has no intensity. At 1 intensity 1, and so 4. Let the verticals drop from the slanting line stand for the sensations aroused. At 0 there will be no sensation. At 1 there will be a sensation represented by the length of the vertical at 1. At 2 the sensation will be represented by s squared 2, and so on. The line of s's will rise evenly because, by the hypothesis, the verticals, or sensations, increase at the same rate as the horizontals, or stimuli, which they severally correspond. But in nature, as aforesaid, they increase at slower rate. If each step forward in the horizontal direction be equal to the last, then each step upward in the vertical direction will have to be somewhat shorter than the last. The line of sensations will be convex on top instead of straight. Fig. 2 represents this actual state of things, 0 being the 0 point of the stimulus and conscious sensation, represented by the curved line, not beginning until the threshold is reached, at which the stimulus is the value 3. From here onwards the sensation increases, but it increases less at each step, until at last, the acme being reached, the sensation line grows flat. The exact law of retardation is called Weber's law from the fact that he first observed it in the case of weights. I'll quote one's account of the law and of the facts on which it is based. Every one knows that in the stilly night we hear things unnoticed in the noise of day. The gentle ticking of the clock, the air circulating through the chimney, the cracking of the chairs in the room, 1,000 other slight noises, impress themselves upon our ear. It is equally well known that in the confused hubbub of the streets, or the clamor of a railway, we may lose not only what our neighbor says to us, but even not hear the sound of our own voice. The stars which are brightest at night are invisible by day, and although we see the moon, and she is far paler than at night. Every one who has had to deal with weights knows that if to a pound in the hand a second pound be added, the difference is immediately felt, whilst if it be added to a hundredweight, we are not aware of the difference at all. The sound of the clock, the light of the stars, the pressure of the pound, these are all stimuli to our senses, and stimuli whose outward amount remains the same. What then do these experiences teach? Evidently nothing but this, that one and the same stimulus, according to the circumstances under which it operates, will be felt either more or less intensely, or not felt at all. Of what sort, now, is the alteration in the circumstances upon which this alteration in the feeling may depend? On considering the matter closely, we see that it is everywhere of one and the same kind. The tick of the clock is a feeble stimulus for our auditory nerve, which we hear plainly when it is alone, but not when it is added to the strong stimulus of the carriage wheels and other noises of the day. The light of the stars is a stimulus to the eye, and if the stimulation which this light exerts be added to the strong stimulus of daylight, we feel nothing of it, although we feel it distinctly when it unites itself with the feebler stimulation of the twilight. Pound weight is a stimulus to our skin, which we feel when it joins itself to a preceding stimulus of equal strength, but which vanishes when it is combined with a stimulus 1,000 times greater in amount. We may therefore lay it down as a general rule that a stimulus, in order to be felt, may be so much the smaller if the already pre-existing stimulation of the organ is small, but must be so much the larger, the greater the pre-existing stimulation is. The simplest relation would obviously be that the sensation should increase in identically the same ratio as the stimulus. But if this simplest of all relations prevailed, the light of the stars, e.g., ought to make as great an addition to the daylight as it does to the darkness of the nocturnal sky, and this we know to be not the case. So it is clear that the strength of the sensations does not increase in proportion to the amount of the stimuli, but more slowly. And now comes the question, In what proportion does the increase of the sensation grow less as the increase of the stimulus grows greater? To answer this question, everyday experiences do not suffice. We need exact measurements, both of the amounts of the various stimuli and of the intensity of the sensations themselves. How to execute these measurements, however, is something which daily experience suggests. To measure the strength of sensations is, as we saw, impossible. We can only measure the difference of sensations. Experience showed us what very unequal differences of sensation might come from equal differences of outward stimulus. But all these experiences express themselves in one kind of fact, that the same difference of stimulus could in one case be felt, and in another case not felt at all. A pound felt if added to another pound, but not if added to a hundredweight. We can quickest reach a result with our observations if we start with an arbitrary strength of stimulus, notice what sensation it gives us, and then see how much we can increase the stimulus without making the sensation seem to change. If we carry out such observations with stimuli varying absolute amounts, we shall be forced to choose in an equally varying way the amounts of addition to the stimulus which are capable of giving us a just barely perceptible feeling or more. A light to be just perceptible in the twilight need not be near as bright as the starlight. It must be far brighter to be just perceived during the day. If now we institute such observations for all possible strengths of the various stimuli, and note for each strength the amount of addition of the latter required to produce a barely perceptible alteration of sensation, we shall have a series of figures in which is immediately expressed the law according to which the sensation alters when the stimulation is increased. Observations according to this method are particularly easy to make in the spheres of light, sound, and pressure. Beginning with the latter case, we find a surprisingly simple result. The barely sensible addition to the original weight must stand exactly in the same proportion to it, be the same fraction of it, no matter what the absolute value may be of the weights on which the experiment is made. As the average of a number of experiments, this fraction is found to be about 1/3, that is, no matter what pressure there may already be made upon the skin, an increase or a diminution of the pressure will be felt as soon as the added or subtracted weight amounts to 1/3 of the weight originally there. One then describes how differences may be observed in the muscular feelings, in the feelings of heat, in those of light, and in those of sound, and he concludes thus: so we have found that all the senses whose stimuli we are enabled to measure accurately obey a uniform law. However various may be their several delicacies of discrimination, this holds true of all, that the increase of the stimulus necessary produce an increase of the sensation bears a constant ratio to the total stimulus. The figures which express this ratio in the several senses may be shown thus in tabular form. Sensation of light, 1 of 100 muscular sensation, 1 of 17 feeling of pressure, 1/3 warmth, 1/3 sound, 1/3. These figures are far from giving as accurate a measure as might be desired, but at least they are fit to convey a general notion of the relative discriminative susceptibility of the different senses. The important law which gives in so simple a form the relation of the sensation to the stimulus that calls it forth was first discovered by the physiologist Ernst Heinrich Weber to obtain in special cases. Fechner's law. Another way of expressing Weber's law is to say that to get equal positive additions to the sensation, one must make equal relative additions to the stimulus. Professor Fechner of Leipzig founded upon Weber's law a theory of the numerical measurement of sensations, over which much metaphysical discussion has raged. Each just perceptible addition to the sensation, as we gradually let the stimulus increase, was supposed by him to be a unit of sensation, and all these units were treated by him as equal, in spite of the fact that equally perceptible increments need by no means appear equally big when they once are perceived. The many pounds which form the just perceptible addition to a hundredweight feel bigger when added than the few ounces which form the just perceptible addition to a pound. Fechner ignored this fact. He considered that if n distinct perceptible steps of increase might be passed through in gradually increasing a stimulus from the threshold value till the intensity S was felt, then the sensation of S was composed of n units, which were of the same value all along the line. Sensations once represented by numbers, psychology may become, according to Fechner, an exact science susceptible of mathematical treatment. His general formula for getting at the number of units in any sensation is S equals C log R, where S stands for the sensation, R for the stimulus numerically estimated, and C for a constant that must be separately determined by experiment in each particular order of sensibility. The sensation is proportional to the logarithm of the stimulus, and the absolute values, in units, of any series of sensations might be got from the ordinates of the Curve in Fig 2, if it were a correctly drawn logarithmic curve with the thresholds readily plotted out from experiments. Fechner's psychophysic formula, as he called it, has been attacked on every hand, and as absolutely nothing practical has come of it, it need receive no farther notice here. The main outcome of his book has been to stir up experimental investigation into the validity of Weber's law, which concerns itself merely with the just perceptible increase and says nothing about the measurement of the sensation as a whole, and to promote discussion of statistical methods. Weber's law, as will appear when we take the senses seriatim, is only approximately verified. The discussion of statistical methods is necessitated by the extraordinary fluctuations of our sensibility from one moment to the next. It is found, namely, when the difference of two sensations approaches the limit of discernibility, that at one moment we discern it, and at the next we do not. Our incessant accidental inner alterations make it impossible to tell just what the least discernible increment of the sensation is without taking the average of a large number of appreciations. These accidental errors are as likely to increase as to diminish our sensibility, and are eliminated in such an average, for those above and those below the line then neutralize each other in the sum, and the normal sensibility, if there be one, that is, the sensibility, due to constant causes, is distinguished from these accidental ones, stands revealed. The methods of getting the average all have their difficulties and their snares, and controversy over them has become very subtle indeed. As an instance of how laborious some of the statistical methods are, and how patient German investigators can be, I may say that Fechner himself, in testing Weber's law for weights by the so-called method of true and false cases, tabulated, computed no less than 24,576 separate judgments. Sensations are not compounds. The fundamental objection to Fechner's whole attempt seems to be this, that although the outer causes of our sensations may have many parts, every distinguishable degree, as well as every distinguishable quality, of the sensation itself appears to be a unique fact of consciousness. Each sensation is a complete integer. The strong one, as Dr. Munsterberg says, is not the multiple weak one or compound of many weak ones, but rather something entirely new and as it were incomparable, so that to seek measurable difference between strong and weak sonorous, luminous, or thermic sensations would seem at first sight as senseless as to try to compute mathematically the difference between salt and sour, or between headache and toothache. It is clear that if in the stronger sensation of light the weaker sensation is not contained, it is unpsychological to say that the former differs from the latter by certain increment. Surely our feeling of scarlet is not feeling of pink with a lot more pink added. It is something quite other than pink. Similarly with our sensation of an electric arc light, it does not contain that of many smoky tallow candles in itself. Every sensation presents itself as an indivisible unit, and it is quite impossible to read any clear meaning into the notion that they are masses of units combined. There is no inconsistency between this statement and the fact that, starting with weak sensation and increasing it, we feel more as the increase goes on. It is not more of the same stuff added, so to speak, but it is more and more difference, more and more distance from the starting point, which we feel. In the chapter on discrimination, we shall see that difference can be perceived between simple things. We shall see, too, that differences themselves differ. There are various directions of difference, and along any one of them, a series of things may be arranged so as to increase steadily in that direction. In any such series, the end differs more from the beginning than the middle does. Differences of intensity form one such direction of possible increase, so our judgments of more intensity can be expressed without the hypothesis that more units have been added to a growing sum. So-called law of relativity. Weber's law seems only one case of the still wider law that the more we have to attend to, the less capable we are of noticing any one detail. The law is obvious where the things differ in kind. How easily do we forget bodily discomfort when conversation waxes hot? How little do we notice the noises in the room so long as our work absorbs us? Ad plura intentus minus idiot singula sensus, as the old proverb says. One might now add that the homogeneity of what we have to tend to does not alter the result, but that mind with two strong sensations of the same sort already before it is incapacitated by their amount from noticing the detail of difference between them which it would immediately be struck by, were the sensations themselves weaker and consequently endowed with less distracting power. A particular idea may be taken for what it is worth. Meanwhile, it is an undoubted general fact that the psychical effect of incoming currents does depend on what other currents may be simultaneously pouring in. Not only the perceptibility of the object which the current brings before the mind, but the quality of it is changed by the other currents. Simultaneous sensations modify each other, is brief expression for this law. We feel all things, relation to each other, is once vaguer formula for this general law of relativity, which in one shape or other has had vogue since Hobbes's time in psychology. Much mystery has been made of it, but although we are of course ignorant of the more intimate processes involved, there seems no ground to doubt that they are physiological and come from the interference of one current with another. A current interfered with might naturally give rise to a modified sensation. Examples of the modification in question are easy to find. Notes make each other sweeter in accord, and so do colors when harmoniously combined. A certain amount of skin dipped in hot water gives the perception of a certain heat. More skin immersed makes the heat much more intense, although of course the water's heat is the same. Similarly, there is a chromatic minimum of size in objects. The image they cast on the retina must needs excite a sufficient number of fibers, or it will give no sensation of color at all. Weber observed that a thaler laid on the skin of the forehead feels heavier when cold than when warm. Herbenkisch has found that all our sense organs influence each other's sensations. The hue of patches of color so distant as not to be recognized was immediately, in his patients, perceived when a tuning fork was sounded close to the ear. Letters too far off to be read could be read when the tuning fork was heard, etc., etc. The most familiar examples of this sort of thing seem to be the increase of pain by noise or light, and the increase of nausea by all, and common in sensations, effects of contrast. The best known examples of the way in which one nerve current modifies another are the phenomena of what is known as simultaneous color contrast. Take a number of sheets of brightly and differently colored papers, lay on each of them a bit of one and the same kind of gray paper, then cover each sheet with some transparent white paper, which softens the look of both the gray paper and the colored ground. The gray patch will appear in each case tinged by the color complementary to the ground, and so different will the several pieces appear that no observer, before raising the transparent paper, will believe them all cut out of the same gray. Helmholtz has interpreted these results as being due to a false application of an inveterate habit that, namely, of making allowance for the color of the medium through which things are seen. The same thing in the blue light of a clear sky, in the reddish yellow light of a candle, in the dark brown light of a polished mahogany table which may reflect its image, is always judged of its own proper color, which the mind adds out of its own knowledge to the appearance, thereby correcting the falsifying medium. In the cases of the papers, according to Helmholtz, the mind believes the color of the ground, subdued by the transparent paper, to be faintly spread over the gray patch. But a patch to look gray through such colored film would have really to be of the complementary color to the film. Therefore it is of the complementary color, we think, and proceed to see it of that color. This theory has been shown to be untenable by Hering. The discussion of the facts is too minute for recapitulation here, but suffice it to say that it proves the phenomenon to be physiological. Case of the way in which, when sensory and nerve currents run in together, the effect of each on consciousness is different from that which it would be if they ran in separately. Successive contrast differs from the simultaneous variety, and is supposed to be due to fatigue. The facts will be noticed under the head of after images, in the section on vision. It must be borne in mind, however, that after images from previous sensations may coexist with present sensations, and the two may modify each other just as coexisting sensational processes do. Other senses than sight show phenomena of contrast, but they are much less obvious, so I will not notice them here. We can now pass to a very brief survey of the various senses in detail. Chapter 3. Sight. The structure is described in all the books on anatomy. I will only mention the few points which concern the psychologist. It is a flattish sphere formed by a tuft of white membrane, the sclerotic, which encloses a nervous surface and certain refracting media, lens and humors, which cast a picture of the outer world thereon. It is, in fact, a little camera obscura, the essential part of which is the sensitive plate. The retina is what corresponds to this plate. The optic nerve pierces the sclerotic shell and spreads fibers radially in every direction over its inside, forming a thin translucent film the fibers pass into, a complicated apparatus of cells, granules, and branches, and finally end in the so-called rods and cones, which are the specific organs for taking out the influence of the waves of light. Strange to say, these end organs are not pointed forward towards the light as it streams through the pupil, but backwards towards the sclerotic membrane itself, so that the light waves traverse the translucent nerve fibers and the cellular and granular layers of the retina before they touch the rods and cones themselves, the blind spot. The optic nerve fibers must thus be unimpressible by light directly. The place where the nerve enters is in fact entirely blind, because nothing but fibers exist there, the other layers of the retina only beginning round about the entrance. Nothing is easier than to prove the existence of this blind spot. Close the right eye and look steadily with the left at the cross in Fig 6, holding the book vertically in front of the face and moving it to and fro. It will be found that at about foot off the black this disappears, but when the page is nearer or farther, it is seen. During the experiment, the gaze must be kept fixed on the cross. It is easy to show by measurement that this blind spot lies where the optic nerve enters. The fovea. Outside of the blind spot, the sensibility of the retina varies. It is greatest at the fovea, a little pit lying outwardly from the entrance of the optic nerve, and round which the radiating nerve fibers bend without passing over. The other layers also disappear at the fovea, leaving the cones alone to represent the retina there. The sensibility of the retina grows progressively less towards its periphery, by means of which neither colors, shapes, nor number of impressions can be well discriminated. In the normal use of our two eyes, the eyeballs are rotated so as to cause the two images of any object which catches the attention to fall on the two foveae as the spots of acutest vision. This happens involuntarily, as any one may observe. In fact, it is almost impossible not to turn the eyes the moment any peripherally lying object does catch our attention, the turning of the eyes being only another name for such rotation of the eyeballs as will bring the fovea under the object's image. Accommodation. The focusing or sharpening of the image is performed by a special apparatus. In every camera, the farther the object is from the eye the farther forward, and the nearer the object is to the eye the farther backward, is its image thrown. In photographers' cameras, the back is made to slide, and can be drawn away from the lens when the object that casts the picture is near, and pushed forward when it is far. The picture is thus kept always sharp, but no such change of length is possible in the eyeball, and the same result is reached in another way. The lens, namely, grows more convex when a near object is looked at, and flatter when the object recedes. This change is due to the antagonism of the circular ligament in which the lens is suspended, and the ciliary muscle. The ligament, when the ciliary muscle is at rest, assumes such a spread-out shape as to keep the lens rather flat. But the lens is highly elastic, and it springs into a more convex form which is natural to it whenever the ciliary muscle, by contracting, causes the ligament to relax its pressure. The contraction of the muscle, by thus rendering the lens more refractive, adapts the eye for near objects, accommodates it for them, as we say, and its relaxation, by rendering the lens less refractive, adapts the eye for distant vision. Accommodation for the near is thus the more active change, since it involves contraction of the ciliary muscle. When we look far off, we simply let our eyes go passive. We feel this difference in the effort when we compare the two sensations of change. Invergence accompanies accommodation. The two eyes act as one organ, that is, when an object catches the attention, both eyeballs turn so that its images may fall on the fovea. When the object is near, this naturally requires them to turn inwards, or converge, and as accommodation then also occurs, the two movements of convergence and accommodation form naturally associated couple, of which it is difficult to execute either singly. Contraction of the pupil also accompanies the accommodative act. When we come to stereoscopic vision, it will appear that by much practice one can learn to converge with relaxed accommodation and to accommodate with parallel axes of vision. These are accomplishments which the student of psychological optics will find most useful. Single vision by the two retinae. We hear single with two ears, and smell single with two nostrils, and we also see single with two eyes. The difference is that we also can see double under certain conditions, whereas under no conditions can we hear or smell double. The main conditions of single vision can be simply expressed. In the first place, impressions on the two fovea always appear in the same place. By no artifice can they be made to appear alongside of each other. The result is that one object, casting its images on the fovea of the two converging eyeballs, will necessarily always appear as what it is, namely one object. Furthermore, if the eyeballs, instead of converging, are kept parallel, and two similar objects, one in front of each, cast their respective images on the fovea, the two will also appear as one, or, in common parlance, that their images will fuse. To verify this, let the reader stare fixedly before him as if through the paper at infinite distance, with the black spots in Fig 8 in front of his respective eyes. He will then see the two black spots swim together, as it were, and combine into one, which appears situated between their original two positions and as if opposite the root of his nose. This combined spot is the result of the spots opposite both eyes being seen in the same place. But in addition to the combined spot, each eye sees also the spot opposite the other eye. To the right eye this appears to the left of the combined spot. To the left eye it appears to the right of it, so that what is seen is three spots, of which the middle one is seen by both eyes, and is flanked by two others, each seen by one. That such are the facts can be tested by interposing some small opaque object so as to cut off the vision of either of the spots in the figure from the other eye. A vertical partition in the median plane, going from the paper to the nose, will effectually confine each eye's vision to the spot in front of it, and then the single combined spot will be all that appears. If, instead of two identical spots, we use two different figures, or two differently colored spots, as objects for the two fovi to look at, they still are seen in the same place, but since they cannot appear as single object, they appear there alternately displacing each other from the view. This is the phenomenon called retinal rivalry. As regards the parts of the retinae round about the fovi, similar correspondence obtains. Any impression on the upper half of either retina makes us see an object as below, on the lower half as above, the horizon, and on the right half of either retina, an impression makes us see an object to the left, on the left half one to the right of the median line. Thus each quadrant of one retina corresponds as whole to the geometrically similar quadrant of the other, and within two similar quadrants, and are, for example, there should, if the correspondence were carried out in detail, be geometrically similar points which, if impressed at the same time by light emitted from the same object, should cause that object to appear in the same direction to either eye. Experiment verifies this surmise. If we look at the star evolved with parallel eyes, the stars all seem single, and the laws of perspective show that under the circumstances the parallel light rays coming from each star must impinge on points within either retina which are geometrically similar to each other. Similarly, pair of spectacles held an inch or so from the eye seem like one large median glass, or we may make an experiment like that with the spots. If we take two exactly similar pictures, no larger than those on an ordinary stereoscopic slide, and if we look at one with each eye median partition confining the view, we shall see but one flat picture, all of whose parts appear single, identical. Retinal points being impressed, both eyes see their object in the same direction, and the two objects consequently coalesce into one. Here again retinal rivalry occurs if the pictures differ, and it must be noted that when the experiment is performed for the first time the combined picture is always far from sharp. This is due to the difficulty mentioned on page 33 of accommodating for anything as near as the surface of the paper, whilst at the same time the convergence is relaxed so that each eye sees the picture in front of itself. Double images. Now it is an immediate consequence of the law of identical location of images falling on geometrically similar points that images which fall upon geometrically disparate points of the two retinae should be seen in disparate directions, and that their objects should consequently appear in two places, or look double. Take the parallel rays from star falling upon two eyes which converge upon your object. Instead of being parallel, as in the previously instanced case, the two fovi will receive images of O, which therefore will look single. If then, as seen in Fig. 10 be the parallel rays, each of them will fall upon the nasal half of the retina which it strikes. But the two nasal halves are disparate, geometrically symmetrical, not geometrically similar. The star's image on the left eye will therefore appear as if lying to the left of O. Its image on the right eye will appear to the right of this point. The star will, in short, be seen double, homonymously double. Conversely, if the star be looked at directly with parallel axes, any near object like O will be seen double, because its images will affect the outer or cheek halves of the two retinae instead of one outer and one nasal half. The position of the images will here be reversed from that of the previous case. The right eye's image will now appear to the left, the left eye's to the right. The double images will be heteronymous. The same reasoning and the same result ought to apply where the object's place with respect to the direction of the two optic axes is such as to make its images fall not on non-similar retinal halves, but on non-similar parts of similar halves. Here, of course, the positions seen will be less widely disparate than in the other case, and the double images will appear to lie less widely apart. Careful experiments made by many observers according to the so-called aploscopic method confirm this law, and show that corresponding points, a single visual direction, exist upon the two retinae. For the detail of these one must consult the special treatises. Vision of solidity. This description of binocular vision follows what is called the theory of identical points. On the whole, it formulates the facts correctly. The only odd thing is that we should be so little troubled by the innumerable double images which objects near and farther than the point looked at must be constantly producing. The answer to this is that we have trained ourselves to habits of inattention in regard to double images. So far as things interest us, we turn our fovi upon them, and they are necessarily seen single, so that if an object impresses disparate points, that may be taken as proof that it is so unimportant for us that we needn't notice whether it appears in one place or in two. By long practice, one may acquire great expertness in detecting double images, though, as someone says, It is an art which is not to be learned completely either in 1 year or in 2. Where the disparity of the images is but slight, it is almost impossible to see them as if double. They give rather the perception of a solid object being there. To fix our ideas, take Fig 11. Suppose we look at the dots in the middle of the lines, and be just as we looked at the spots in Fig 8. We shall get the same result that will coalesce in the median line, but the entire lines will not coalesce, for owing to their inclination, their tops fall on temporal and their bottoms on the nasal, retinal halves. What we see will be 2 lines crossed in the middle. The moment we attend to the tops of these lines, however, our foci tend to abandon the dots and to move upwards, and in doing so to converge somewhat following the lines, which then appear coalescing at the top, as in Fig 13. If we think at the bottom, the eyes descend and diverge, and what we see is Fig 14 running our eyes up and down the line, makes them converge and diverge just as they would were they running up and down some single line whose top was nearer to us than its bottom. Now, if the inclination of the lines be moderate, we may not see them double at all, but single throughout their length when we look at the dots. Under these conditions, their top does look nearer than their bottom. In other words, we see them stereoscopically, and we see them so even when our eyes are rigorously motionless. In other words, the slight disparity in the bottom ends which would draw the foci divergently apart makes us see those ends farther. The slight disparity in the top ends which would draw them convergently together makes us see these ends nearer than the point at which we look. The disparities, in short, affect our perception as the actual movements would, the perception of distance. When we look about us at things, our eyes are incessantly moving, converging, diverging, accommodating, relaxing, and sweeping over the field. Subjectively considered, distance is an altogether peculiar content of consciousness. Convergence, accommodation, binocular disparity, size, degree of brightness, parallax, etc. all give us special feelings, which are signs of the distance feeling, but not it. They simply suggest it to us. The best way to get it strongly is to go upon some hilltop and invert one's head. The horizon then looks very distant and draws near as the head erects itself again. The perception of size. The dimensions of the retinal image determine primarily the sensations on which conclusions as to size are based, and the larger the visual angle, the larger retinal image. Since the visual angle depends on the distance of an object, the correct perception of size depends largely upon correct perception of distance. Having formed judgment, conscious or unconscious, as to that, we conclude as to size from the extent of the retinal region affected. Most people have been surprised now and then to find that what appeared large bird in the clouds was only small insect close to the eye, the large apparent size being due to previous incorrect judgment as to the distance of the object. The presence of an object of tolerably well-known height as man also assists in forming conceptions. By comparison, as to size, the artists for this purpose frequently introduce human figures to assist in giving an idea of the size of other objects represented. Sensations of color. The system of colors is a very complex thing. If one take any color, say green, one can pass away from it in more than one direction through a series of greens more and more yellowish, let us say, towards yellow, or through another series more and more bluish towards blue. The result would be that if we seek to plot out on paper the various distinguishable tints, the arrangement cannot be that of a line, but as to cover a surface with tints arranged on a surface we can pass from any one of them to any other by various lines of gradually changing intermediaries. Such an arrangement is represented in Fig. 15. It is a merely classificatory diagram based on degrees of difference simply felt, and has no physical significance. Black is a color, but does not figure on the plane of the diagram. We cannot place it anywhere alongside of the other colors because we need both to represent the straight gradation from untinted white to black, and that from each pure color towards black as well as towards white. The best way is to put black into the third dimension beneath the paper E.g. as is shown perspectively in Fig. 16. Then all the transitions can be schematically shown. One can pass straight from black to white, or one can pass round by way of olive, green, and pale green, or one can change from dark blue to yellow through green, or by way of sky blue, white, and straw color, etc. In any case, the changes are continuous, and the color system thus forms what one calls a tridimensional continuum. Color mixture. Physiologically considered, the colors have this peculiarity, that many pairs of them, when they impress the retina together, produce a sensation of white. The colors which do this are called complementaries. Such are spectral red and green blue, spectral yellow and indigo blue. Green and purple, again, are complementaries. All the spectral colors added together also make white light, such as we daily experience in the sunshine. Furthermore, both homogeneous ether waves and heterogeneous ones may make us feel the same color when they fall on our retina. Thus yellow, which is a simple spectral color, is also felt when green light is added to red. A blue is felt when violet and green lights are mixed. Purple, which is not a spectral color at all, results when the wave either of red and of violet or those of blue and of orange are superposed. From all this it follows that there is no particular congruence between our system of color sensations and the physical stimuli which excite them. Each color feeling is a specific energy, P11, which many different physical causes may arouse. Helmholtz, Hering, and others have sought to simplify the tangle of the facts by physiological hypotheses which differ much in detail, agree in principle, since they all postulate a limited number of elementary retinal processes to which, when excited singly, certain fundamental colors severally correspond. When excited in combination, as may be by the most various physical stimuli, other colors, called secondary, are felt. The secondary color sensations are often spoken of as if they were compounded of the primary sensations. This is a great mistake. The sensations as such are not compounded. Yellow, for example, a secondary on Helmholtz's theory, is as unique a quality of feeling as the primaries red and green, which are said to compose it. What are compounded are merely the elementary retinal processes. These, according to their combination, produce diverse results on the brain, and thence the secondary colors result immediately in consciousness. The color theories are thus physiological, not psychological, hypotheses, and for more information concerning them the reader must consult the physiological books. The duration of luminous sensations. This is greater than that of the stimulus, a fact taken advantage of in making fireworks. An ascending rocket produces sensation of a trail of light extending far behind the position of the bright part of the rocket itself at the moment, because the sensation aroused by it in a lower part of its course still persists, so shooting stars appear to have luminous tails behind them by rotating rapidly before the eye. A disk with alternate white and black sectors we get for each point of the retina alternate stimulation due to the passage of white sector and rest when a black sector is passing. If the rotation be rapid enough, the sensation aroused is that of a uniform gray, such as would be produced if the white and black were mixed and spread evenly over the disk. In each revolution the eye gets as much light as if that were the case, and is unable to distinguish that this light is made up of separate portions reaching in at intervals. The stimulation due to each lasts until the next begins, and so all are fused together. If one turn out suddenly the gas in a room containing no other light, the image of the flame persists a short time after the flame itself is extinguished. If we open our eyes instantaneously upon a scene and then shroud them in complete darkness, it will be as if we saw the scene and ghostly light through the dark screen. We can read off details in it which were unnoticed whilst the eyes were open. This is the primary positive afterimage, so called. According to Helmholtz, 1/3 of a second is the most favorable length of exposure to the light for producing it. The nervous visual apparatus is easily fatigued. Usually we do not observe this because its restoration is also rapid, and in ordinary life our eyes, when open, are never at rest. We move them to and fro so that parts of the retina receive light alternately from brighter and darker objects, and are alternately excited and rested. How constant and habitual the movement of the eyes is can be readily observed by trying to affix for a short time a small spot without deviating the glance, and to do so for even a few seconds is impossible without practice. If any small object is steadily affixed for 20 or 30 seconds, it will be found that the whole field of vision becomes grayish and obscure, because the parts of the retina receiving most light get fatigued and arouse no more sensation than those less fatigued and stimulated by light from less illuminated objects, or look steadily at a black object, say a blot on a white page, for 20 seconds, and then turn the eye on. A white wall of the latter will seem dark gray, with a white patch on it, an effect due to the greater excitability of the retinal parts previously rested by the black, when compared with the sensation aroused elsewhere by light from the white wall acting on the previously stimulated parts of the visual surface. All persons will recall many instances of such phenomena, which are especially noticeable soon after rising in the morning. Similar things may be noticed with colors, that after looking at a red patch the eye turned on a white wall sees a blue-green patch of the elements causing red sensations having been fatigued. The white mixed light from the wall now excites on that region of the retina only the other primary color sensations. The blending of colors so as to secure their greatest effect depends on this fact. Red and green go well together because each rests the parts of the visual apparatus most excited by the other, and so each appears bright and vivid as the eye wanders to and fro, while red and orange together, each exciting and exhausting, mainly the same visual elements, render dull, or in popular phrase kill, one another. If we fix steadily for 30 seconds a point between two white squares about 4 millimeters, 1/6 inch, apart on large black sheet, and then close and cover our eyes, we get negative after image in which are seen two dark squares on brighter surface. This surface is brighter closer around the negative after image of each square, and brightest of all between them. This luminous boundary is called the corona, and is explained usually as an effect of simultaneous contrast. The dark after image of where it is said makes us mentally in judgment and think the clear surface close to it brighter than elsewhere, and it is brightest between the two dark squares, just as middle-sized man between two tall ones looks shorter than if alongside one only. If, however, the after image be watched, it will often be noticed not only that the light band between the squares is intensely white, much more so than the normal ideoretinal light, see below, but as the image fades away, often the two dark after images of the squares disappear entirely with all of the corona, except that part between them which is still seen as bright band on uniform grayish field. Here there is no contrast to produce the error of judgment, and from this and other experiments Heron concludes that light acting on one part of the retina produces inverse changes in all the rest, and that this plays an important part in producing the phenomena. Similar phenomena may be observed with colored objects. In their negative after images each tint is represented by its complementary, as black is by white and colorless vision. This is one of the facts referred to on p. 27 which have made Heron reject the psychological explanation of simultaneous contrast. The intensity of luminous objects. Black is an optical sensation. We have no black except in the field of view. We do not, for instance, see black out of our stomach or out of the palm of our hand. Pure black is, however, only an abstract idea, for the retina itself, even in complete objective darkness, seems to be always the seat of internal changes which give some luminous sensation. This is what is meant by the ideoretinal light, spoken of a few lines back. It plays its part in the determination of all after images with closed eyes. Any objective luminous stimulus to be perceived must be strong enough to give a sensible increment of sensation over and above the ideoretinal light. As the objective stimulus increases, the perception is of an intenser luminosity, but the perception changes more slowly than the stimulus. The latest numerical determinations, by Koenig and Broadhun, were applied to 6 different colors and ran from an intensity arbitrarily called 1 to 1, which was 100,000 times as great. From intensity 2,000 to 20,000, Weber's law held good. Below and above this range, discriminative sensibility declined. The relative increment discriminated here was the same for all colors of light, and lay, according to the tables, between 1 and 2% of the stimulus. Previous observers have got different results. A certain amount of luminous intensity must exist in an object for its color to be discriminated at all. In the dark all cats are gray, but the colors rapidly become distincter as the light increases, first the blues and last the reds and yellows, up to a certain point of intensity, when they grow indistinct again through the fact that each takes a turn towards white. At the highest bearable intensity of the light, all colors are lost in the blinding white dazzle. This again is usually spoken of as a mixing of the sensation white with the original color sensation. It is no mixing of two sensations, but the replacement of one sensation by another in consequence of a changed neural process. This has been part 1 of Psych for Psychology's reading of Psychology by William James. Thanks for listening.